Welcome back to the series on statistics. In this video, we're going to be talking about the Central Limit Theorem, which is a very powerful theorem in statistics. It's utilized in a lot of different applications. I have it listed here. This might not be the way it's written everywhere, but this is the way I've chosen to write it. We have a proposition that tells us if we have n independent and identically distributed random variables, each with a mean of mu and a standard deviation of sigma, then what the Central Limit Theorem tells us is that if we take the limit of the number of these random variables as it approaches infinity, then the mean of those random variables will be normally distributed with a mean of mu and a standard deviation of sigma divided by the square root of n. Now, the reason that this theorem is so useful is because of sampling. You can imagine each one of these random variables as an observation or sample of a population. In that context, so long as our sampling method was consistently independent and random, then this would follow this assumption here that we have n independent and identically distributed random variables, because each one of these samples would follow the probability distribution of the population with which you are sampling, and these mean and the standard deviation here would just be the mean and standard deviation of the population. So each one of these random variables would be independent and identically distributed according to the probability distribution of the population with respect to the context of sampling some larger population. And so in that context, what the Central Limit Theorem would tell us is that as our sample size tended towards infinity, then our sampling distribution, or the distribution of sampled means, would be normally distributed with a mean of mu and a standard deviation of sigma divided by the square root of our sample size. And so that's a useful fact that we want to get to. I have some notes here. So the first paragraph just tells us exactly what I just said. But one of the things that's very important to keep in mind there is that obviously you can't have an infinite sample size. And so the point is that although that can't be carried out to fruition according to the Central Limit Theorem directly, you could imagine that at some point there will be some sample size that's sufficiently large for us to at least say that our distribution of sampled means will be approximately normal. And then what that allows us to do is to make several statements about our population based only on our sample data. And we can make those statements based off of the probability density function or the cumulative density function of the normal distribution, which we know how to work with. We've derived that. We know how to deal with that mathematically. And so that's where the power of the Central Limit Theorem comes from, is really right there. And so if we want to sort of visualize this idea, I have this graph here. I think we've briefly touched on something like this before, but this is just some graph I found on the internet. It's from a Medium article where they used a computer program to simulate sampling these different distributions. They plotted their sampled distributions, or the distribution of sampled means here in these bottom 8 graphs. And as you can see, it doesn't matter what our original population distribution looks like. It could be normally distributed, uniformly distributed, skewed. It could follow some sort of random distribution that doesn't seem to have some sort of pattern. It really doesn't matter what these population distributions look like, because as we increase our sample size, you can see that the distribution of sample means appears to be more and more normal. Additionally, you could see that it seems to be less and less spread out, our distribution of sample means. As you can see, the width of these graphs tends to shrink. So that supports this idea that the standard deviation of our sampling distribution will be inversely proportional to the sample size in some way here according to the square root. And so this visualization, which was based on a computer program, does seem to support this idea, but we still want to formally prove it. It's just a little visualization. Also, you can sort of see these graphs here on the bottom. This is the distribution of the sampled means for a sample size of 30. Even just at this point, these look very, very normal. And so you can imagine that there seems to be some point which, at least according to this, doesn't seem to be that large. I mean, 30 is a very feasible, reasonable sample size to be conducting, where our sample distribution appears to be approximately normal. And so we don't actually need an infinite sample size to make these statements with a very large degree of accuracy. And now I do have an additional cautionary message here, which is that I've heard this many times. It's very common to misinterpret the meaning of the Central Limit Theorem. We're not saying that as the sample size tends towards infinity, our sample is going to look more and more normal. That doesn't make any sense. Our sample is based off of the population distribution. It's going to look more and more like the population distribution, if anything. What we're referencing with the Central Limit Theorem is the distribution of sampled means as our sample size increases. So it's a very important distinction. And if you want to have any more information about what the distribution of sampled means actually is, I do have some video on that, specifically on the distribution of sampled means or the sampling distribution. So I'd recommend watching that if you are confused about that idea. So with that background out of the way, let's get into the business of actually proving the central limit theorem. I don't think this theorem is as hard as many people make it out to be to prove, but I do think it is very easy to get lost as to what you're actually doing as you work through the steps of this proof. So I'm going to try to be very clear about what we're doing and why we're doing it for every step along the way as we work our way through this. And so just as a quick example, right off the bat, first thing that we're seeing here is that the proposition is that as the number of these random variables tends towards infinity, their mean will be normally distributed with a mean of mu and a standard deviation of sigma over square root of n. And so we can write this. This is just a concise way of writing this. I guess this would be the variance here. And so this is what the central limit theorem tells us as n goes to infinity. And so this is the central limit theorem. And so the first thing that we're going to do is we're going to make the statement that this is logically equivalent to some new random variable. We'll define a new random variable called z sub n, which is equal to, here we would want the mean minus the mean of the population distribution divided by the population standard deviation, which would be given here. We want to say that this is normally distributed with a mean of 0 and a standard deviation of 1. And we have actually already done this. This was in our video on z-scores. We showed that showing that this expression here is normally distributed according to the standard normal distribution is exactly the equivalent to showing that this random variable here is normally distributed according to this mean and this standard deviation. So if you're at all confused about why these two expressions are logically equivalent, I recommend watching my video on z-scores where I cover this detail here. But this is going to be a lot easier to work with because then all we need to do, ultimately we're going to try to show that the moment generating function for this random variable as n goes to infinity tends towards the moment generating function for the standard normal distribution, which is a lot easier to show than detailing out the normal or the moment generating function for a non-standard normal distribution. So it's going to be easier to work with this. And so that's our first step here, is that we want to work with this random variable. And then we can sort of expand this out, because you can imagine that our x bar here is the mean of all of these random variables, and that's just the sum divided by the number of random variables, which is n. And I'll be clear here, I'll add that as n goes to infinity. And so if we sort of expand this out and multiply the top and bottom of this fraction by our sample size, so to speak, or our n here, then what we'll get is that z sub n, we're just multiplying the top and bottom by n. On the top, we'll get the sum from I is equal to 1 to n of x sub I minus mu. Because here, then if you were to expand out the sum, there would be n of these negative mu's, and so it would be minus n mu. And so this is exactly the same. And then we would be dividing the sum by, and then here when we multiply by n, we're going to get sigma times the square root of n. And this, if we can sort of manipulate this just a little bit, if we were to pull out this square root of n, then this would be 1 over the square root of n multiplied by the sum, I is equal to 1 to n of x sub I minus mu divided by the standard deviation here. Let me be clear, this is an I. Now this might look familiar from my video on z-scores, or if you're familiar with the z-scores, but this is just the normalization of this random variable, because here, if we have that this random variable has a mean of mu and a standard deviation of sigma, then applying this transformation to these random variables will just change it to where this is a mean of 0 and a standard deviation of 1. And so it will be a lot easier to work with this. And another thing we could do, similar to when we define this new random variable, we could define a random variable here as well. Since this is just a transformation of that random variable, we can call this y sub I and say that this is equal to x sub I minus mu divided by our standard deviation. And it will actually be a lot easier to work with this. It wasn't strictly necessary to pull out this factor here of 1 over the square root of n. I just wanted to highlight that this is exactly just a normalization process. And so I'm going to pull that square root of n back in, but I did want to make that point. And so if we make this substitution here, then this condenses quite nicely. into the sum from I is equal to 1 to n of y sub I over the square root of n. And now, as we outlined at the beginning, what we want to do is try to find the moment generating function of this random variable here as n tends towards infinity. But an important step along the way will just be finding the moment generating function for this random variable. And so if we want to find the moment generating function for z sub n, we know how to find the moment generating function. For the definition, this is just the expected value of e to the power, or here, e to the power s times, and then here I'll just plug in the sum of some sort of dummy variable. Here I'll just use y sub I, just in keeping with the notation. I'll just use a lowercase y. But we want to incorporate all of these random variables. And so here we have y sub I over the square root of n. And so this is what our moment generating function is for this random variable. It's just according to the definition. But you can imagine, since we have the sum here, we can sort of move this s in, and we can distribute this out. And so just according to the laws of exponents, this would just be equal to the expected value of, and then here, this would be the product from I is equal to 1 up to n of e to the power of s y sub I over the square root of n. Here, this is all in the exponent. Now, since we have that each of these random variables, x sub I, x sub 1, x sub 2, x sub all of them, they're all independent and identically distributed. Because they're independent, then y sub I is also going to be independent, and all of these y's will be independent and identically distributed random variables. And since these y sub i's are going to be independent, then we can apply this expectation operator across this product. And so we could say by independence, we have that this is equal to the product from I is equal to 1 to n of the expected value of e to the power of s times y sub I over n. And now here, this expression looks strikingly familiar to this expression looks strikingly familiar to our definition of the moment generating function. And indeed, this is actually just equal to the moment generating function of y. But here, since we have this factor, this should be a square root here. Since we have this factor of a square root of n, which is just a transformation, this is just equal to the moment generating function of y, but instead of being evaluated at s here, we're evaluating at s over the square root of n. And if that's confusing, you can think of just just placing the square root of n under this s. It's exactly the equivalent. And so that's what this expected value expression here is equal to. And the key thing to realize here is that if these y's are also independent and identically distributed random variables, and then for each one of these, since they're identically distributed, they should have the same moment generating function. And so all of these moment generating functions for each one of these random variables y's, y sub 1, y sub 2, because they're identically distributed, will just be equal to this moment generating function for y, some general moment generating function, and I'm just going to notate it as the moment generating function for the random variable y. And since we're just taking the product from I is equal to 1 up to n, this is just this expression multiplied by itself n times, and so this is exactly equivalent to the moment generating function for y evaluated at s over the square root of n. All of this is going to be to the power of n. So I went ahead and filled in that reasoning here. We're talking about we make this leap by the definition of the moment generating function and the fact that they're identically distributed. And so now we sort of shortened our workload a lot, because now we just really need to find the moment generating function for y. In the definition of the moment generating function, as we previously utilized it, the moment generating function for y, this is just the expected value of e to the s y. Now, we could sort of expand this out by Taylor's theorem. And if we expand out that exponential, then this becomes equal to the expected value. Then just expanding that out, we get 1 plus sy squared over 2 factorial, and then this pattern will proceed. Now, what we can realize is that this expectation operator is linear, and so this is going to be equal to the expected value of 1 plus the expected value of sy, and then we would proceed this out, and then this is just equal to the expected value of 1 is just 1, and then we can do plus s times the expected value of y. Because this is a linear operation, the expectation is linear, and so I'm going to write that soon, but I'm just going to finish out this reasoning, and then this is going to be plus s squared over 2 factorial times the expected value of y squared. And this will continue out, and we could say by the linearity of expectation. Oops. Now we appear to have hidden sort of a wall in our reasoning here, because we still have these expected values here. But the key thing to realize is that although we don't know much about the distribution of x1, x2, all the way up to xn, nor the distribution for x or y sub I, what we do know is that the first moment here, because we've defined this as the normalization of the random variable x, we're subtracting off the mean. The first moment of this, or the expected value of the random variable y, should be 0, and the second moment should be equal to the variance, since the second moment is equal to, or the second moment minus the first moment squared is equal to our variance, and the second moment is equal to 1, or our variance is equal to 1, and our first moment is equal to 0, then that implies that our second moment, or the expected value of y squared, should be equal to 1. And so we don't know much about this random variable, but we do know what its first and second moments are. And so that's just equal to these expected values here. This is the first moment, which we just determined is equal to 0, just by the definition of this random variable y. And then this second moment here is going to be equal to 1. Once again, just from that definition. And so what we'll find is that this will cancel, and that this is just going to be equal to 1. And so what we'll get is that the moment generating function of y with respect to s will just equal, here we would have 1 plus, we'd have s squared over 2 factorial times the expected value of y squared, which is just equal to 1. And then for the remainder of this, we're going to have infinitely many terms, but I'm just going to write the rest of this as in summation notation. And so this will go from, let's see, we would have k is equal to 3, or I guess I use I because I used that before, from I is equal to 3 all the way up to infinity. And then what would we have here? We'd have s to the power of I over I factorial multiplied by the expected value of y to the power of I. Y to the power of I. And so this is equal to our moment generating function of y. And now one key thing to note here before we move forward is what is going to be the limit of this expression here, just this summation. I guess I should be more clear. This summation right here as s tends towards 0. What's the limit as s tends towards 0 of this summation here from I is equal to 3 all the way to infinity of s to the power of I over I factorial multiplied by the expected value of, or the ith moment of y. And so what's the limit of this as s tends towards 0? It should be pretty obvious here, but we have an s in the numerator that's going to tend towards 0, so this would just be 0 times something. And so this is just going to be the sum of infinitely many zeros, but that's just equal to 0. And so the reason that we want to know what this limit is because we're not actually interested specifically in the moment generating function of y evaluated at s. We're interested in the moment generating function, if we recall from up here. Where was it? We're interested in this right here, the moment generating function of y evaluated at s over the square root of n. And ultimately what we're going to be doing is taking the limit as n goes to infinity, and so the limit of s over the square root of n as n goes to infinity will be equal to 0. And so this is going to become relevant. And so now what we have is that the moment generating function of z sub n is just going to equal the moment generating function of y we established before, evaluated at s over the square root of n, that whole expression to the power of n. But now we have an expression for the moment generating function of y, and so we just need to plug s over the square root of n in here everywhere for where we see an s in this expression here. And so this is just going to be equal to 1 plus s over the square root of n squared over 2. And then the conventional way that people notate this is, instead of writing out this entire sum here, the easier way to do it is just to say let h of s be a function that's equal to this sum right here. It's just equal to the sum. And then we could just write this as plus h of s. Or I guess plus h of s over the square root of n. The reason this is easier to look at is just, that should be obvious. But here we know that the limit of this function here, this h of s, is just going to be the limit of this summation as s goes to 0. And we know what that is. And so this is just a much more condensed way of writing this. And so now we are almost done. We just want to show that the limit as n approaches infinity of the moment generating function of z sub n is equal to the limit as n approaches infinity of this expression right here. I'm just going to copy and paste this. Actually, I'm not, because I'm going to rewrite it just a little bit differently. We have 1 plus, and then I can move this out. So this would be s squared over 2. I'm going to rewrite this in this manner, over n, because here we're squaring this. And then here, this is going to be, as n goes to infinity, this s over the square root of n, this is going to go to 0. So this is going to be plus h of 0 to the power of n. And we know that if we take the limit of this function here, this h of s, as s goes to 0, we know that this approaches 0. And so we can rewrite this as the limit as n approaches infinity of 1 plus s squared over 2, s squared over 2 over n to the power of n. Some of you will probably recognize why I've chosen to write this as s squared over 2 over n. This right here, this is just the definition. This limit of this expression as n goes to infinity, this is just the definition of e to the power of s squared over 2. And this right here, this is the moment generating function for a standard normal distribution. And so if the moment generating function of this random variable is equal to the moment generating function of the standard normal distribution, then we have just proven thus that z sub n is normally distributed, the mean of 0 and a variance of 1. And thus from that it follows, because this is logically equivalent to the x bar, or the mean of our random variables, being normally distributed with a mean of mu and a standard deviation, or a variance of sigma squared over n. And so we've just proven this, which is logically equivalent to this. And so we have proven that this is true as, I guess we should add, as n towards infinity, tends towards infinity. All right, so that concludes my proof of the central limit theorem using just moment generating functions. We didn't have to dive into characteristic functions to prove this. I hope this is formal enough. I think you might need to show that this summation here is a well-defined function, but I think it follows from the fact if you accept that this entire sum is a well-defined function, then it's pretty clear that this is also a well-defined function. I don't want to get too far away from the point in this video, so I hope you accept this proof as formal enough. But I do want to return to this idea here that I outlined in these notes, which is that all we've proven here is that if we take if you want to think about the context of a sample of a population, what we've proven in this here is that as our sample size tends toward infinity, then the distribution of sampled means is normally distributed with a mean of mu and a variance of sigma squared over n. But I want to talk about this approximate normal distribution that we're going to get as our sample size increases. How big of a sample size do we need for this to be approximately normal? Now, this is actually a matter of this is somewhat subjective. It's going to depend on how your population is constructed. There's no specific sample size that we can give that is going to tell you when it will be approximately normal or about how normal it will be. All of that will depend a little bit, at least to some extent, on the population you're dealing with. And if the population distribution that you're dealing with is unknown, as it commonly is, then there's not really anything you can do to guarantee that it will be normal to the extent that you need it to be, or normal to the extent of the accuracy that you need. And so this is where we get into the principles of experimental design. But as a general rule of thumb, many people say that the cutoff here is the sample size of 30. So as if your sample size is at least 30, and 30 or greater than that, then it's very commonly accepted that your distribution of sampled means will be approximately normal. And you can use the tools of the probability density function or the cumulative density function for the normal distribution to describe your sampling distribution. And so that rule of n being greater than or equal to 30 is very commonly heard in statistics. And so when we're dealing with hypothesis testing or confidence intervals, which will be that's going to be coming down the pipeline very soon, when we're dealing with that, that's very, very often there's going to be this condition of normality that we need to have in order to ensure that we can use these tools to analyze our sample data. And so that's a very conventional cutoff. But I do want to emphasize that is not, like, there's no particular reason why n is equal to 30 is specifically chosen. Or at least there was nothing I was able to find that showed, like, oh, if you have a sample size of 30, then you're ensuring that your error it will be within some boundary based on your population distribution. I have never found anything on the internet or anything in any of my textbooks that indicates that that's true. This appears to just be a convention. So I want to emphasize that. And good principles of experimental design would demand that you, maybe in certain situations you need a much larger sample size, and maybe in other situations you need less of a sample size. For example, if you know that your population distribution is normal, if you know that, then you can get away with a smaller probability or a smaller sample size, because your probability distribution will be, or your distribution of sampled means will follow the distribution of your population in that case, which is normal, and so you could already use those tools regardless of your sample size. And so these are just some things to think about. But I hope that was interesting. I hope this proof was easy enough to follow. Hope it's illuminating. Hope you guys enjoyed, and I'll see y'all in the next video when I finally talk about how to conveniently solve these problems with which we need the normal distribution. I do think it was important to talk about this first, though, because this is sort of telling us why the normal distribution is so useful, is because it allows us to deal with sampling, which is almost always what we're dealing with when we're talking about statistics. So you will see these tools come up very frequently. Thank you guys for watching. I'll see you at the next one.